We remember the years by the storms they delivered. 2005 brought Katrina. 2017 unleashed Harvey, Irma, and Maria. And in 2020, the list of names was exhausted, forcing meteorologists to turn to the Greek alphabet for only the second time in history. These represent three of the most destructive hurricane seasons in recent memory. But a quiet and deeply unsettling fact connects them to our present moment. The Atlantic Ocean, at the dawn of each of those historic seasons, was cooler than it is right now. This is not a forecast, but an observation of the current state, a setup that is already in place. It raises a critical question. What occurs when a familiar atmospheric trigger is pulled, but the system is charged with more energy than in those catastrophic years? If these initial conditions give you pause, we invite you to explore them further with us here on Calm Space. As new data and anomalies emerge, we will continue to document the unfolding story of our planet's oceans. The official start of the 2026 Atlantic hurricane season is still more than a month away, yet a peculiar story is already being told by the ocean itself. In the waters off the coast of West Africa, conditions are more typical of August than late April. The warmth is so pronounced that if a meteorologist were to examine a map of sea surface temperatures without a date, they would almost certainly assume they were looking at the peak of the storm season, not the quiet of spring. This is the fundamental reality we must grasp. The ocean is not gradually warming in preparation for the season. Instead, the season is set to arrive in an ocean that is already brimming with the kind of thermal energy that has historically fueled the most powerful and memorable storms. The scientists and forecasters who analyze this data daily at the National Hurricane Center, Colorado State University, and the European modeling centers are not given to alarmism. Panic is not part of their professional protocol, and yet a distinct note of unease has entered their public discussions, a level of caution that has not been apparent for a very long time. It is a subtle but significant signal. When the people who dedicate their lives to observing these systems begin to choose their words with such deliberate care, it suggests that the rest of us should listen closely to what they are seeing. Let us now turn our attention to the very data that is commanding their focus. The vast expanse of tropical water, known as the Main Development Region, stretching from West Africa to the Caribbean, serves as the primary nursery for the Atlantic's most formidable hurricanes. At present, this entire corridor is registering temperatures that are multiple standard deviations above the long-term average. While the term standard deviation may sound like a dry statistical concept, it is a powerful tool for measuring how unusual an event is. In a normal distribution, about 95% of all data points fall within 2 standard deviations. To be 3 standard deviations away from the norm places an event in the outer 0.3%, making it a roughly 1 in 1000 occurrence. We are witnessing conditions that, statistically, should be extraordinarily rare, yet they are becoming a recurring feature of our world. The situation in the Caribbean appears even more anomalous. Here, the ocean heat content a measure of the total thermal energy stored in the water column, which we will explore more deeply later, is shattering every available record in our modern instrumental history. This is not merely a record for the month of April, which would be concerning enough on its own. The current energy readings from the Caribbean are comparable to the levels typically observed only at the absolute zenith of hurricane season in late September. The ocean, it seems, is operating on a timeline 4 months ahead of our calendar. This brings us to a central thesis that must be stated clearly. The narrative for the coming season is not simply that it will be above average. That phrase, while technically accurate, may be misleading, as it implies we are still operating within the bounds of historical experience, just on the warmer end of the spectrum. What the data appears to show is something structurally different. The very starting line has shifted. The fundamental baseline from which we measure has been altered, and every comparison we make to past seasons must be viewed through this new, uncomfortable lens. Herein lies the tension of this moment. The 2026 season has not yet begun. No tropical storm has formed, no hurricane has spun up, and not a single name has been assigned. By all conventional metrics, the season exists only as a projection on paper. And yet, the energy budget, the raw, physical fuel required for hurricanes to ignite and sustain themselves, is already in place. The kindling has been laid, awaiting a spark. It is for this reason that when forecasters search for historical analogues, their analysis consistently returns to the same three pivotal years: 2005, 2017, and 2020. Even if the years themselves are not immediately familiar, the names of the storms they produced are etched into our collective memory. 2005 was the year of Katrina, Rita, and Wilma, a season so relentless it exhausted the alphabetical list of names and required the use of Greek letters for the first time. 2017 gave us Harvey, which stalled over Houston and delivered more than 50 inches of rain. Alongside Irma, a Category 5 that tore through the Caribbean and the Florida Keys, and Maria, which inflicted a blow upon Puerto Rico, from which the island is still recovering. Then came 2020, the season that set a new record with 30 named storms, exhausted the name list for the second time in 15 years, and brought the rapid-fire succession of Laura, Eta, and Iota. Now, we arrive at the crucial pivot point, the single fact that reframes this entire discussion. Each of those three landmark seasons, 2005, 2017, and 2020, emerged from an Atlantic Ocean that was cooler than the one we are observing today. The waters that fed Hurricane Katrina were less warm than the waters of the basin right now. The ocean that intensified Hurricane Maria held less thermal energy than the ocean today. The sea that spawned a record-breaking 30 storms was cooler than the sea today. This reality leaves us with a profound and unavoidable question, one that hangs over this entire pre-season period. Are we still operating within the known and predictable envelope of history, or have we crossed into a new, uncharted climate regime? Have we quietly crossed a threshold into a new reality, where the most severe seasons of our recent past are no longer the exception, but perhaps the new standard? It is helpful to visualize the current climate system as a loaded weapon. While the metaphor is unsettling, its precision is undeniable. The mechanism is primed, the chamber is full, yet the trigger remains untouched for now. Whether this potential is unleashed depends on a confluence of factors we will explore in detail. The timing of El Niño, the behavior of high-altitude wind patterns, the quantity of dust carried from the Sahara, and the wave trains originating off the coast of Africa, these are the elements that could pull the trigger. But the system is already loaded, and it holds more potential energy than at any point in our recorded history. Over the next 4 sections, we will carefully dissect this situation piece by piece. We will examine why the ocean failed to undergo its typical winter reset. We will investigate the depth of this oceanic heat, as satellite imagery reveals only the surface of the story. We will then turn to the atmospheric configuration, the timing of El Niño, and the variables that even the most advanced models cannot forecast more than a few weeks ahead. Finally, we must confront the most disquieting possibility, that the historical seasons we use as benchmarks may no longer be sufficient to define what is truly possible. It is crucial to understand that this analysis is not a prediction. No one, not here at Calm Space, not the National Hurricane Center, not even the most sophisticated supercomputer in Europe can state with certainty in April how many hurricanes will make landfall in the United States this year. That is simply not how the science operates. What we can do, and what scientists undertake at this time every year, is a process of pattern recognition. We observe the current conditions and compare them to the conditions of past years that produced extreme outcomes. We then assess the degree of overlap. What this comparison is revealing right now is that 2026 exhibits every key ingredient that fueled the most destructive seasons in modern records. And yet, it possesses something more, an additional factor lurking beneath the surface that none of those analog years had. The critical question to hold in mind, therefore, is not whether this season will be active. The present setup suggests that an active season is almost a certainty. The more profound question is whether the historical analogues we rely on will be enough to contain what is possible. Because if they are not, if 2026 is beginning from a starting point that 2005, 2017, and 2020 never experienced, then we are not merely anticipating a bad season. We may be facing the first season that requires a descriptive language we have not yet had to invent. To understand why, we must begin with the most fundamental inquiry of all. Why did the ocean not cool down? Part 2. The ocean's failed reset. Every winter, the Atlantic Ocean is meant to perform a specific vital function. It is supposed to release heat. The mechanics behind this process are well understood. As the sun shifts southward, the days grow shorter and the winds strengthen. Large extratropical storm systems, unrelated to hurricanes, churn across the North Atlantic from October through March. This action mixes the warm surface water with cooler layers from below. Heat radiates upward into the atmosphere and is also carried away by ocean currents. In essence, the ocean exhales the vast energy it accumulated during the summer. By the time spring arrives, the basin has largely been returned to a baseline state, its thermostat turned back down. Then, as summer approaches and the sun's intensity increases, the cycle begins anew. This is the established rhythm, the way the system has operated for as long as we have possessed the instruments to measure it. The winter serves as the reset, wiping the slate more or less clean so that the upcoming hurricane season must build its energy reserves from something close to scratch. However, the winter of 2025 into 2026 did not follow this script. While the processes that normally expel heat from the ocean did occur, they did so with nowhere near their usual efficiency. Consequently, the ocean entered the spring of 2026 bearing a thermal signature that, in any other year, one would not expect to see until late May at the earliest, and in some regions, not until June. Let the significance of that settle in for a moment. The ocean did not begin its seasonal warming from a neutral starting point. It began with a substantial surplus. As the seasonal warming process accelerates through the spring, with the sun climbing higher and the days lengthening, it is not building up heat from a baseline. It is adding new energy on top of an already historic surplus. This means that by the official start of hurricane season on June 1st, the entire basin will be resting on a thermal foundation that, in the past, would have been achievable only in the middle of summer. This is what scientists refer to as thermal carryover. The heat from the previous season was not fully exported. It persisted, rolled forward, and is now compounding with the new heat being added by the spring sun. A financial analogy illustrates this phenomenon quite well. Imagine you have a savings account that is designed to reset to zero every January. Now, imagine that this year, instead of resetting, it carried over a balance, and that balance was the largest ever recorded. Then, your normal monthly deposits begin to arrive on top of that unprecedented starting amount. By the end of the year, you would not have a normal balance. You would have a sum that the bank has never witnessed before. There is also a longer-term piece of this story that is essential for understanding the foundation we are operating from. Since approximately 1995, the Atlantic has been in what climate scientists call the warm phase of the Atlantic multi-decadal variability, or AMV. Without delving into its complex mechanics, the AMV is a slow, natural oscillation in North Atlantic sea surface temperatures, swinging between a warm phase and a cool phase over periods of roughly 20 to 40 years. When the AMV is in its warm phase, Atlantic hurricane seasons generally tend to be more active. Conversely, when it is in its cool phase, they are typically quieter. The shift into the warm phase in the mid-1990s is a major reason why the late 1990s, 2000s, and 2010s were so much more active than the relatively calm decades that preceded them. So, part of what we are witnessing, the elevated baseline and the generally warm Atlantic, is simply the AMV behaving as expected. That has been the case for 30 years and is not, in itself, new. What is new, and what is so concerning, is the sheer magnitude of the current warmth. The AMV helps explain why the baseline is warm, but it does not account for why the baseline is this times warm. This critical distinction tells us that while a known cycle has set the stage, another factor is amplifying conditions to a level we have never seen before. The current temperature anomaly in the Atlantic is soaring far above the levels predicted by the Atlantic multidecadal oscillation alone. It seems clear that another phenomenon is layered on top of this natural cycle, one that is amplifying the warm phase beyond its historical boundaries. A growing body of evidence points to a critical, yet often overlooked, piece of this puzzle. It appears that the vertical mixing within the Atlantic Ocean has become less efficient in recent years. This is the vital process that transfers heat from the surface down into the colder depths, away from the air-sea interface. The ocean is becoming more stratified, with a layer of warm water resting on top of cooler water, resisting the urge to mix. When this occurs, heat that would typically be drawn downward is instead trapped near the surface. This is a development with profound consequences, as it means this energy remains available for a developing hurricane to use. Even if the total heat within the basin had remained unchanged, this redistribution alone, concentrating warmth at the surface, would significantly increase the potential energy for tropical storms. Of course, the total heat content has not stayed the same. It has been steadily rising. This means we are facing two compounding factors. There is more heat overall, and a greater portion of it is concentrated right where storms can access it. Adding to this complex picture is the Atlantic Meridional Overturning Circulation, or AMOC. This vast system of currents, which includes the Gulf Stream, acts as a planetary conveyor belt, transporting warm water from the tropics northward and cold water from the poles southward. It is one of Earth's primary engines for redistributing heat. A substantial amount of research now suggests that the AMOC has been weakening over the last several decades. While the reasons for this are a deep topic for another time, the immediate consequence is straightforward. A less vigorous AMOC is less effective at exporting heat out of the tropics, causing more of that warmth to be retained in the very regions where hurricanes are born. This is precisely the trend we are observing. When these powerful forces are considered in unison, a clearer picture emerges. The AMV is in its warm phase, vertical mixing has grown less efficient, and the AMOC appears to be slowing. Each of these factors, on its own, would be enough to explain a warmer tropical Atlantic. Together, they reveal why the basin entered the 2026 season already in a supercharged state. This brings us back to a central, unavoidable conclusion. The starting line for hurricane season has fundamentally shifted. We are not talking about a change of a few days, but potentially weeks or even months. The oceanic conditions observed in late April are now what we would have expected to see well into the summer in previous decades. The ocean did not have a chance to reset over the winter, which means that in a meaningful, energetic sense, the season did not begin in June. It began months ago. The fuel is already in place, and has been for some time. All that is missing is the spark. Yet, to focus only on the temperature of the ocean's surface is to see just one dimension of the story. If the analysis stops there, it misses the most dangerous element of the current conditions. The true signal, the one that is causing deep concern among forecasters, is not visible in the satellite data you can view online. It lies hidden from sight, deep within the ocean. This is the inherent limitation of satellite imagery. It is, by its nature, a measurement of the surface. Those striking, color-coded maps that show angry red blotches of sea surface temperature across the tropics are depicting the very skin of the ocean, sometimes only the top few millimeters. And while that surface temperature is absolutely critical, hurricanes undeniably need warm surface water to form, it does not provide the complete picture. In fact, it may not even be the most crucial part. The most important factor is what is happening beneath, in the layers that cannot be seen from space. To truly grasp the situation, specialists in tropical cyclones turn to a different metric, a concept known as ocean heat content. The term may sound technical, but its meaning is quite direct. Ocean heat content is simply a measure of the total amount of thermal energy stored in a column of seawater, from the surface down to a specific depth. While surface temperature tells you how hot the very top layer is, ocean heat content reveals how much fuel is stacked in the layers below. Why is this distinction so vital? Because a hurricane is a vast heat engine, and its interaction with the ocean is incredibly dynamic. As a storm moves, it doesn't just skim heat from the surface. Its powerful winds churn the water beneath it, mixing the upper ocean. Under normal circumstances, this churning process serves as a natural break. As a hurricane stirs the ocean, it pulls cooler water up from the depths. This upwelling mixes with the warm surface water, causing the temperature directly under the storm to drop. In effect, the fuel supply becomes diluted. The storm, having undermined its own source of energy, is forced to weaken. This negative feedback has historically been a key factor in limiting the ultimate intensity of tropical cyclones. The storm draws power from the ocean, and the ocean responds by offering a cooler version of itself, forcing the storm to either lose strength or move on to find a fresh patch of warm water. It is one of the planet's built-in mechanisms to prevent hurricanes from intensifying indefinitely. But what if this fundamental safety mechanism were to fail? Imagine a scenario where a storm churns the ocean to a depth of 100 meters, only to find that the water it pulls up is just as warm as the water at the surface. In this case, the feedback loop breaks down entirely. The storm churns and churns, but instead of diluting its fuel, it only draws up more warm water. The energy supply never runs out. Instead of self-limiting, the storm just keeps drinking from a seemingly endless reservoir of heat. This is the danger posed by deep layers of warm water, and it is precisely why ocean heat content is a far better predictor of a hurricane's potential intensity than surface temperature alone. This is not a hypothetical scenario. It is the reality unfolding right now in the Caribbean and within the loop current. The warmth does not stop at the surface. It extends deep into the water column, reaching depths of 100 meters, 150 meters, and in some areas, even more. The 26 degrees Celsius isotherm, the depth at which the water cools to 26 degrees, roughly the minimum temperature needed to sustain a hurricane, is now sitting deeper than at any point in our instrumental records. The ocean's reserve of fuel is, by all available metrics, unprecedented. To make this tangible, consider the current state of the Western Caribbean. In some areas, one would need to descend over 100 meters before the water temperature falls below the critical threshold that powers a major hurricane. This represents a column of exceptionally warm water as high as a 30-story building. It is a vast reservoir of thermal energy, a latent power source simply waiting for a trigger. A key feature in this system, one that has played a central role in some of the most destructive hurricanes on record, is the loop current. This powerful current is effectively a river of warm tropical water flowing north from the Caribbean Sea and into the Gulf of Mexico. It then loops back around before exiting through the Florida Straits, where it feeds into the Gulf Stream. Periodically, this current sheds large, spinning eddies, enormous pinwheels of warm water that detach from the main flow and drift slowly westward across the Gulf. The implications of this process for storm development are profound. When a hurricane moves over one of these eddies, it experiences a sudden and dramatic surge of energy, much like an engine receiving a sudden injection of high-octane fuel. Because this pocket of warmth extends so deep, the storm's own churning fails to bring cold water to the surface, disabling the natural cooling feedback that would normally limit its power. This very pattern has been observed time and again. In 2005, Hurricane Katrina intensified with explosive speed when it traversed a loop current eddy in the central Gulf. Just weeks later, Hurricane Rita followed a similar, devastating path of intensification. More recently, in 2021, Hurricane Ida escalated from a Category 1 to a Category 4 storm in less than a day while passing over the warm waters near the Louisiana coast. The formula is tragically consistent. A hurricane combined with deep, warm water often results in rapid and sometimes terrifying growth. What sets the 2026 season apart is the sheer scale of these conditions. In previous analog years we often look to, such as 2005, 2017, and 2020. These features of deep, warm water were localized phenomena. The loop current and its specific eddies were dangerously warm, creating hazardous pockets where a storm could find the fuel for extreme intensification. The rest of the basin, however, remained relatively normal. A storm crossing one of these features received a boost, but one that missed them had to contend with more typical, self-limiting conditions. What we are witnessing now is a fundamental shift where those once localized conditions have become basin-wide. The deep, warm water that was previously confined to the loop current and a few associated eddies is now present across most of the Caribbean, large portions of the Gulf of Mexico, and even into the western Atlantic. This changes the entire dynamic of the season. Consequently, storms that form or strengthen in this environment will not be searching for occasional pockets of energy. Instead, they will be moving through an ocean where high-octane fuel is uniformly available at depth, no matter where they travel. This is why the central question for this season is no longer about whether storms will form. The conditions almost guarantee their genesis. The far more critical question is what these storms will become once they exist. The continuity of this energy, an unbroken supply of fuel, from the surface down to significant depths, is now more consistent across the basin than at any other time in the instrumental record. This has direct and alarming implications for a phenomenon we will explore in greater detail later: rapid intensification. This is the process by which a tropical storm can escalate into a major hurricane in under 24 hours, and it has emerged as the single most dangerous trend in modern tropical meteorology. To better understand this shift, an analogy might be helpful. Picture a simple candle. Its wick is saturated with a small amount of wax. When you light the candle, the flame consumes the wax in the wick, which in turn slowly draws more fuel up from the candle's body. The flame's intensity is limited by the speed at which the wax can travel up the wick. If you were to try and force the flame to burn faster, you would simply exhaust the available fuel in the wick, and the flame would shrink until more wax could be drawn upward. This is how a hurricane typically operates, with the warm surface water acting as the wax in the wick. Now, imagine a different kind of candle, one where the wick is connected directly to a large tank of fuel. The wax no longer needs to travel up a wick. The fuel is simply there, available in a seemingly unlimited supply, ready to be burned as fast as the flame can consume it. In this scenario, the flame is no longer limited by its fuel source. Its only constraint is how quickly it can draw oxygen from the surrounding air. This second scenario is what a hurricane in the 2026 Atlantic Basin might look like. The wick, representing the thin layer of surface heat, has effectively been replaced by a direct fuel line connected to a deep reservoir. The natural cooling feedback mechanism has been broken. The energy supply is no longer a shallow layer that storms must use carefully, but a deep, vast reserve that does not easily run out. So, to return to our central thread, the ocean is loaded with an unprecedented amount of energy. We have established that it is warmer than in any comparable analog year in recorded history. And now, we add a second, crucial piece to the puzzle. This heat is not just a surface-level phenomenon, it is layered. It extends deep into the water column, and it is structurally configured in a way that maximizes the potential energy available to any tropical system that forms. This means that the historical comparisons we might make to years like 2005, 2017, and 2020 must be adjusted. It is not just the surface heat that is different, but the depth of that heat. The fundamental dynamic has shifted, as if the slow-burning candles of the past have been replaced by direct fuel lines. And yet, an ocean by itself does not create hurricanes. An ocean is merely potential energy. You can have all the fuel in the world, but if the atmosphere above is not cooperative, that potential will never be realized. Hurricanes require specific wind patterns to organize their structure, sufficient moisture in the right locations, and, critically, the absence of strong upper-level winds that would tear them apart. They need an atmospheric trigger. Therefore, we must now turn our attention away from the ocean and look upward into the sky. The second half of this story unfolds in the atmosphere, and what is happening there right now is giving forecasters every bit as much cause for concern as the conditions in the water below. You have likely heard of El Niño and La Niña, perhaps in the context of weather forecasts, or as the cause for everything from droughts in California to floods in Peru. These phenomena are part of a larger climate pattern known as the El Niño Southern Oscillation, or ENSO. In the context of the Atlantic, they are arguably the single most important factor influencing hurricane activity. It is for this reason that we must discuss the current state of ENSO. Where this powerful global pattern stands at this exact moment is one of the primary reasons that forecasters are watching this season with such profound unease. The state of the tropical Pacific is often defined by a simple trio of conditions: the warmth of El Niño, the coolness of La Niña, or the neutrality that lies between them. But it is not the state itself that commands our attention today. It is the trajectory. The path of change is where the true peril often lies, and the current trajectory mirrors a pattern seen in years that produced some of the most destructive hurricane seasons on record. For much of the past year, the tropical Pacific has been under the influence of La Niña. The Oceanic Niño Index, which provides a smoothed measurement of sea surface temperatures in this critical region relative to the long-term average, registered a value of approximately negative 0.55. This figure indicates a moderate La Niña. Since then, a rapid warming has taken hold. The index has surged to around negative 0.16, lifting the Pacific out of La Niña and into the warmer side of neutral. The trend is unmistakably upward, and the ocean is moving toward El Niño with remarkable speed. This is where a delicate and dangerous balance begins. The transition from La Niña, or neutral conditions, toward a full-blown El Niño represents what is empirically the most threatening configuration for an Atlantic hurricane season. This is not some marginal effect. It is a central observation drawn from decades of seasonal forecasting research. As the Pacific warms, but before it becomes truly warm, the Atlantic is granted a window of opportunity. During this period, the suppressive effects of a mature El Niño have not yet materialized, while the favorable conditions from the preceding La Niña or neutral state linger. It is a unique and precarious setup, combining the worst atmospheric elements of both worlds into a single season. It is no mere coincidence that the three analog years we continually reference 2005, 2017, and 2020 all shared this exact dynamic. Each of these years was transitional. In all three instances, the Pacific was either emerging from La Niña or was in an early neutral phase, clearly on a path toward a different state. And in each of those years, the Atlantic basin responded with explosive activity. This historical parallel provides a stark warning about the potential that lies ahead. The underlying mechanism is quite direct. A fully developed El Niño typically acts to suppress hurricane activity in the Atlantic. It achieves this primarily by altering upper-level wind patterns across the tropics, which generates significant wind shear. This phenomenon, which involves changes in wind speed or direction with height, is the natural enemy of hurricanes, tearing their vertical structure apart. El Niño also shifts the position of the Atlantic high-pressure system and modifies moisture patterns, creating an environment less conducive to the organization of tropical disturbances. On balance, a strong El Niño is bad news for hurricanes, or rather, good news for those in their path. However, a crucial delay exists in this system. The atmosphere does not react instantly to the warming of the Pacific Ocean. First, the ocean must warm significantly. Then, that warmth must be sustained long enough to fundamentally alter the patterns of convection, the large-scale rising and falling of air. Only after these patterns are established can their influence ripple across the globe through vast atmospheric chains of cause and effect known as teleconnections. It is only at the end of this long process that the suppressive effects, like increased wind shear, begin to manifest over the Atlantic. This entire sequence can take many months to unfold. During that interval, while the Pacific is warming but the atmosphere has yet to catch up, the Atlantic basin behaves as if El Niño is not yet a factor. From an atmospheric perspective, it isn't. The suppressive signals have not propagated across the planet, and the wind shear has not increased. The basin continues to operate under the rules of the previous state. For 2026, that previous state was La Niña, which is characterized by low wind shear and conditions highly favorable for hurricane development. This suggests that for the early and middle parts of the season, the Atlantic will likely feature an atmospheric setup that historically fosters high activity. This is the essence of what can be called transitional instability. The climate system is shifting, but the change is incomplete, creating a hybrid state with elements of both La Niña and El Niño. For the months when Atlantic hurricanes pose the greatest threat, August, September, and into October, this configuration could leave the basin without the natural breaks that a fully formed El Niño would normally provide. Adding another layer of complexity is the sheer speed of this transition. Moving from a moderate La Niña to the warm side of neutral in such a short period is an unusually fast pace. Rapid ENSO transitions are notoriously difficult for seasonal forecasting models to handle. When ENSO is moving quickly, these models struggle to project its evolution over the next 6 months, resulting in wider error bars and a broader range of possible outcomes. This means that even the experts who create these forecasts are operating with reduced confidence. When all these factors are combined, a deeply concerning picture emerges. We have a transitional state that is historically favorable for storms, a transition occurring at an unusually high speed, and historical analogues that point to the worst seasons in modern memory. The result is a setup that is both favorable and unstable. It is favorable for hurricanes, as the conditions for their formation and intensification are primed, and it is unstable, as the timing and impact of El Niño's eventual influence remain profoundly uncertain. Here, we must return to the central thread of our narrative. The point is not simply that ENSO is in a transitional phase. The point is that it is in a specific phase that has historically produced the most devastating Atlantic hurricane seasons we have ever witnessed. It is the same trigger configuration that gave us the seasons of Katrina, Maria, and the year that exhausted the standard list of storm names. And this trigger is now being applied to an Atlantic Ocean that is warmer and contains more energy than it did in any of those previous analog years. This is the situation. This is what the data is telling us right now. This brings us to a crucial element of the puzzle and a common point of confusion when considering the link between El Niño and hurricane seasons. Many people, upon hearing that an El Niño is forming, assume it will lead to a suppressed hurricane season. While this isn't entirely incorrect, it isn't precisely right either. The reality is far more nuanced, and it is within this complexity that the true danger resides. It is a subtlety that can have profound consequences. Part 5. The shear illusion. A widely held belief often circulates in popular discussions about hurricanes, and it generally follows this logic. El Niño suppresses hurricane activity, while its counterpart, La Niña, enhances it. Consequently, the news of a developing El Niño might bring a sense of relief, suggesting a quieter hurricane season ahead. This is one of those statements that is accurate in its broad strokes but dangerously misleading in its specifics. And it is the specifics that matter most. It is worth taking a moment to clarify what actually happens, because this is an area where the gap between public perception and operational reality can have very real consequences. At the heart of this dynamic is a concept known as wind shear. In the context of tropical cyclones, this term describes the variation in wind speed and direction at different altitudes over a specific area. When wind shear is low, the winds throughout the atmospheric column are moving in a similar direction and at a similar speed. This stable environment allows hurricanes to organize themselves. The immense columns of thunderstorms that form a hurricane's core can align vertically, allowing the powerful heat engine within to operate efficiently. The storm can build its eye wall and intensify. Conversely, when wind shear is high, the opposite occurs. Strong winds in the upper atmosphere can effectively shear the tops off of developing thunderstorms. This process tilts the storm's vertical structure, disrupting the organization that a hurricane requires to strengthen. The system is torn apart faster than it can build itself. In short, high wind shear is a hurricane killer. It acts as a natural brake on a storm's development. One of the most significant effects of a fully developed El Niño in the Pacific is that it tends to increase wind shear over the tropical Atlantic. So, it is true that in a year with a mature El Niño, the Atlantic typically experiences more shear, which in turn usually leads to fewer hurricanes. This is the basis for the conventional wisdom. But this is precisely where the popular understanding begins to falter. The increased shear does not manifest the moment the Pacific begins to warm. Instead, it appears only after the global atmosphere has had time to fully adjust to the warmer ocean temperatures. This atmospheric adjustment is not instantaneous. It involves a significant lag, often taking several months. In some cases, the protective shear doesn't truly establish itself over the Atlantic until well into the autumn, long after El Niño has been in place. In a year like 2026, which finds us in the early phases of a transition from neutral conditions toward a warmer state, this atmospheric response will be delayed. While the Pacific is warming, the wind patterns over the Atlantic are still operating in a configuration much closer to their previous state. The wind shear is not yet high. In many regions, it remains low, creating an environment that is still favorable for hurricane development. And these favorable conditions could persist for some time, potentially through the entire climatological peak of the hurricane season. This phenomenon is what we might call the shear illusion. People hear that El Niño is on its way and assume it means a quiet season is guaranteed. But an approaching El Niño and an El Niño that is exerting its full atmospheric influence are two very different things, often separated by a crucial period of several months. During that interval, the Atlantic basin behaves as if El Niño isn't a factor yet, because from an atmospheric standpoint, it isn't. To put this in more concrete terms, let's look at the calendar. The Atlantic hurricane season officially runs from June 1st through November 30th. The climatological peak, the period that accounts for over 70% of all major hurricane activity, is a concentrated 8-week window from roughly mid-August to mid-October. This is the window that truly defines the character of a season. If we find ourselves in late April with an El Niño just beginning to emerge, the critical question for forecasters becomes whether that El Niño will be developed enough by mid-August to begin suppressing storm activity. The honest answer at this stage is that it probably will not. It is possible that suppressive effects could begin to appear by late September or October, but not before. This timing suggests that the most active part of the season is likely to unfold during a window when El Niño's calming influence has not yet meaningfully arrived. This situation is known within the forecasting community as seasonal window misalignment. The term refers to scenarios where the favorable and unfavorable conditions for hurricane activity are out of sync with the traditional climatological calendar. In a typical El Niño year, the unfavorable conditions, the high wind shear, align with the peak of the season, which is why those years are often quiet. But in years like 2026, the unfavorable conditions are projected to arrive after the peak has already passed. This means the peak occurs without any significant atmospheric breaks. The fuel from warm oceans is there, the atmospheric triggers are favorable, and the shear is low. By the time El Niño actually begins to exert its influence, the most destructive part of the season may have already passed. History provides stark reminders of this misalignment. In 2017, an El Niño was part of the long-term forecast, and many assumed it would moderate the season. But the timing was off. The wind shear suppression did not arrive until late in the season, well after hurricanes Harvey, Irma, and Maria had already caused immense damage. The influence of El Niño did arrive, in a sense, on schedule. It just arrived after the season's most devastating chapter had already been written. A similar pattern unfolded in 2005. For most of that hurricane season, the Pacific was in a transitional state. As a result, wind shear remained low through August, September, and October. By the time any meaningful suppression might have begun to develop, the season had already produced Katrina, Rita, and Wilma, along with a list of named storms, so long it exhausted the standard alphabet and required the use of Greek letters. The pattern is consistent. The mistake is assuming that the calendar of El Niño's development matches the calendar of the hurricane season. It does not. There is a lag, and it is within this critical gap that some of history's most memorable seasons occur. It is important here to stay disciplined and pull this back to the central thread, as it's easy to get lost in the atmospheric mechanics. The point is not just that there is a delay in the El Niño signal. The crucial insight is what this lag means for the 2026 hurricane season in particular. It means the peak of the season is likely to coincide with a window of low atmospheric shear, all occurring over an ocean that is warmer and holds more heat energy than in any comparable year on record. The atmospheric trigger window, that crucial time when conditions become ideal for storms to form and strengthen, appears set to align perfectly with the period when the ocean holds its maximum reserves of energy. It is as if two powerful clocks are ticking towards a single, synchronized moment. When they converge, the result could be the kind of hurricane season we have been exploring. Yet, one must always ask, could this forecast be mistaken? It is possible. An early arrival of El Niño or the timely appearance of atmospheric shear could moderate the season's peak. The atmosphere has certainly defied our models before. But for now, the historical patterns, the analog data, and the current trajectory all point toward the same sobering conclusion. The height of the 2026 season seems destined to unfold within a perfect window of opportunity for hurricanes, and the breadth of that window will ultimately decide if the season is merely bad, profoundly destructive, or something for which we do not yet have a name. Even with this convergence, there is another layer of complexity to consider, a factor that instills a sense of humility in even the most experienced forecasters. This is because no matter how deeply we understand the large-scale climate signals, or how precisely we measure the ocean's state, there are elements within this vast system that remain stubbornly unpredictable beyond a few weeks. These are variables that operate on much shorter timescales than any seasonal forecast can resolve. They have the power to take a perfectly primed environment and either ignite it into a frenzy of storm activity or, on occasion, diffuse the threat. It is here, in the face of these variables, that forecasters must acknowledge a fundamental truth. Even with all the data in the world, some aspects of nature remain genuinely beyond our predictive grasp. These are the wild cards. There exists a dimension of the atmosphere that functions on a rhythm that no seasonal model can truly capture. This is the domain of daily and weekly weather, a part of the system that shifts according to patterns lasting from days to, at most, a couple of months. Within this layer, a small collection of phenomena can interact with the carefully established conditions of ocean temperature, ENSO state, and atmospheric shear. Depending on their behavior, they can either act as a spark, setting the stage ablaze, or serve as a temporary fire blanket, suppressing storm development. These are the wildcards, and a forecast made in April can offer no insight into what they will be doing in September. The first of these unpredictable elements is the Saharan air layer. This is a vast, elevated mass of exceptionally dry and dusty air that originates over the Sahara Desert and is carried westward across the tropical Atlantic. When this layer is active, it hinders hurricane development in two key ways. First, it injects dry air into the storm's circulation, starving a system that thrives on moisture. Second, the dust particles it carries scatter incoming sunlight, which can slightly cool the ocean surface below and weaken the convection that fuels a hurricane's engine. Conversely, when the Saharan air layer is weak, the tropical Atlantic becomes a more humid and favorable environment for storms. The activity of this layer fluctuates on weekly and monthly scales, and its behavior cannot be reliably predicted more than a couple of weeks in advance. The second wildcard is the presence of African easterly waves. These are subtle ripples in the atmosphere that form over the African continent and propagate westward across the Atlantic. They are profoundly important, as they serve as the seed disturbances from which the vast majority of the basin's major hurricanes ultimately grow. If one were to trace the lineage of legendary storms like Katrina, Harvey, or Irma, the trail would eventually lead back to an African easterly wave that departed the coast of West Africa days or even weeks earlier. Some seasons generate a steady procession of strong, well-organized waves, while others produce only weak, disorganized ones that fail to develop. The type of waves that 2026 will feature depends on complex factors over Africa that are simply not foreseeable months ahead of time. Finally, the third wildcard is the Madden-Julian Oscillation, or MJO. The MJO is best described as a slow-moving pulse of weather that travels eastward around the tropics, completing a full circuit roughly every 30 to 60 days. This pulse has two phases, one that enhances cloud formation and rainfall, and one that suppresses it. When the active, enhanced phase of the MJO is positioned over the Atlantic, it creates conditions favorable for tropical cyclone formation. When the suppressed phase is present, it does the opposite. In this sense, the MJO acts like a basin-wide switch, flipping conditions on or off every few weeks. Whether that switch will be in the on position during any given week of the hurricane season's peak is, once again, impossible to know from the perspective of April. Together, these three phenomena, Saharan dust, African waves, and the MJO, represent the variables that operate on timescales too short for seasonal models to resolve. They are the atmospheric noise that overlays the clearer signal of the background climate state. This is precisely why, even in years with the most favorable large-scale setups, the actual storm outcomes can be inconsistent. You can have the most perfect ocean conditions on record and still experience a quiet period in mid-August if the MJO happens to be in its suppressed phase. Likewise, a marginal setup can suddenly produce a major hurricane outbreak if the MJO fires up at just the right moment. These wildcards introduce a genuine, irreducible unpredictability into the system, regardless of how well we understand the underlying conditions. However, and this brings us back to the central theme of our analysis, that unpredictability can work in both directions. This is the crucial point. Even with the influence of these wild cards, the underlying oceanic conditions forecast for 2026 are so supercharged that they surpass anything seen in our analog years. Consequently, when the wild cards do align to favor storm development, the resulting systems will have access to a reservoir of energy far greater than what was available during any previous benchmark season. The roles are distinct but complementary. The wild cards largely determine times when times and times if times storms are able to form. The ocean, however, determines how powerful they have the potential to become once they do. And the ocean of 2026 is projected to hold more thermal energy than any prior baseline can account for. The wildcards, therefore, are not a reason to feel relieved. They are a reason to understand that the variability we are likely to witness will not stem from the underlying setup itself, which is already primed. Instead, the variability will come from the modulation of that setup by these short-term atmospheric phenomena. The system is loaded. The wildcards determine how often the trigger is pulled. But every single time it is pulled, it will be into an ocean that is hotter than any analog year has ever recorded. This means that each storm that successfully forms will have the potential to become far more dangerous than its counterpart would have been in 2005, 2017, or 2020. This leads us to the question that has loomed over this entire discussion. What if our historical analogues are no longer sufficient? What if the comparisons we make, the patterns we match, and the reference points we reach for are simply no longer adequate to describe what the 2026 season is truly capable of producing? To find the answer, we must journey back to those analog years and examine them with fresh eyes. It becomes essential to ask what common threads connected them, and more importantly, what separates the forecast for 2026 from their example. This is because the one variable missing from the comparison, an element that 2026 possesses and its predecessors did not, may prove to be the most significant factor of all. Let us revisit the three historic hurricane seasons that serve as our primary analogues for 2026, but this time from a different vantage point. We will not focus on the specific outcomes of each season. The stories of Katrina, Maria, and the Greek alphabet storms have already been told. Instead, our goal is to distill these years down to the fundamental atmospheric and oceanic conditions they all shared. When you peel away the anecdotal layer of which storm made landfall where, a striking realization begins to emerge. These three seasons, though separated by time, were operating under nearly identical environmental setups. In 2005, the Atlantic multi-decadal variability was in its warm phase, and sea surface temperatures across the basin, especially in the main development region, were significantly above the long-term average. The Pacific was in a transitional state, neither fully La Niña nor neutral. which allowed atmospheric shear over the Atlantic to remain low. With robust African easterly wave activity and a relatively weak Saharan air layer, the stage was set. Multiple favorable phases of the Madden-Julian oscillation passing over the Atlantic during the August to October peak were the final piece. The ocean was warm, the atmosphere was supportive, and the result was 31 tropical cyclones, the most active season ever recorded at the time. This same powerful pattern reappeared in 2017. Once again, the Atlantic multi-decadal variability was in a warm phase, and elevated sea surface temperatures persisted across the main development region for an extended period. The Pacific was shifting from a weak La Niña toward a neutral state, and the disruptive influence of El Niño did not materialize over the Atlantic until late in the season. African easterly waves were strong, and the Madden-Julian oscillation provided productive phases during the season's peak. The consequences of this alignment were catastrophic. We saw Harvey stall over Houston, unleashing biblical rainfall. Irma grew into a devastating Category 5 hurricane that ravaged the Caribbean, and just weeks later, Maria followed, effectively obliterating Puerto Rico's electrical grid for almost a year. It was a season that saw 3 Category 4 or 5 hurricanes make landfall on United States soil or territory. Then came 2020, a year that felt like a haunting echo of the past. The warm phase of the AMV was active, and Atlantic Ocean temperatures were among the warmest ever recorded. The Pacific was transitioning from a weak neutral state into a developing La Niña, a configuration that kept Atlantic shear low and highly conducive to storm formation. African easterly wave activity was once again strong. This confluence of factors produced 30 named storms, the most active season ever documented, exhausting the standard list of names and compelling the use of Greek letters for only the second time in 15 years. Hurricane Laura struck Louisiana as a powerful Category 4, while Hurricanes Eta and Iota both made landfall in Central America as major hurricanes within a span of just 2 weeks. Now, if we observe these 3 seasons together, stripping away the names, the impacts, and the unique personalities of each storm, we are left with a clear 3-part recipe. First, warm Atlantic sea surface temperatures, particularly within the main development region. Second, a favorable phase of the El Niño Southern Oscillation, meaning either La Niña or a transitional neutral state. And third, low wind shear, especially during the early to middle part of the season. That is the core formula. It consists of just 3 ingredients, and history shows that whenever these 3 elements have converged in the same year, the Atlantic Basin has produced a season so extreme that we are still discussing it more than a decade later. This principle is the very foundation of a method known as analog forecasting. The core idea is that if you can identify past years whose large-scale conditions match the conditions of the year you are trying to predict, those past seasons can serve as a valuable guide for what is likely to occur. While it is not a perfect method, no forecasting technique has a long and valid history in seasonal prediction. When the recipe is the same, the outcomes tend to fall within a similar range. Of course, the specific tracks and intensities of individual storms will differ, determined by the unpredictable wildcards we discussed earlier. But the overall character of the season, the total number of named storms, the count of major hurricanes, and the accumulated cyclone energy, these metrics tend to cluster around the historical analogues that share the same underlying environmental state. And this is where the forecast for 2026 becomes so compelling. It matches the recipe. It fulfills all 3 critical ingredients. The AMV is in its warm phase. Atlantic sea surface temperatures are well above average. The Pacific is in that crucial transitional state, moving from La Niña toward a potential El Niño. And by all current indications, early season wind shear is projected to remain low through at least the climatological peak of the season. By every conventional metric of analog forecasting, 2026 aligns perfectly with the most severe seasons in our records. But here, we arrive at the central thread, the crucial inflection point of our entire analysis. The year 2026 does not simply match the recipe, it exceeds it. It contains the same three ingredients, but in greater quantities than any of the analog years ever did. The AMV is warm, but the anomalous warmth layered on top of it is greater than in any previous analog. The Atlantic sea surface temperatures are not just above average, they are soaring to levels that 2005, 2017, and 2020 never reached. The atmospheric shear profile is favorable, but the ocean beneath that calm atmosphere is loaded with a depth of heat, a reservoir of fuel that the analog years simply did not possess. The recipe is the same, but the quantities are different, and this is precisely where the utility of analog forecasting begins to break down. This method operates on the fundamental assumption that the underlying climate system is stationary, that it behaves consistently over time. It assumes that if 2005 and 2026 share the same three ingredients in roughly the same proportions, they should produce a similar outcome. But 2026 does not have the ingredients in the same proportions. It has them in far greater measure. The analog framework, by its very nature, cannot tell us what the result will be when the entire baseline has shifted. We are running the same experiment as in 2005, 2017, and 2020, but this time we are running it with significantly more fuel. So, what does this imply for the season ahead? It means the analog evidence confirms, with a fair degree of confidence, that the recipe is correct. The setup we are observing is precisely the kind of setup that is known to produce extreme seasons. The past tells us that the potential is there. The question that remains is what happens when that potential is amplified beyond anything we have seen before. For the first time, our historical analogs may be incapable of showing us just how extreme a season could become. The reason for this is a fundamental shift in the very foundation of our comparisons. We are no longer measuring new years against a consistent baseline. Instead, the baseline itself is changing, with each recent year sitting on a structurally warmer foundation than the one before it. This raises an uncomfortable question. What if the worst storms of the past no longer represent the ceiling of what is possible? What if they are now closer to the floor? This is the profound challenge that forecasters are grappling with, as their seasonal outlooks depend on ranges derived from historical data. When those historical guideposts begin to lose their relevance, the bounds of prediction become less reliable. A forecast might predict between 15 and 20 named storms, but the very basis for that range was established on a baseline that no longer exists. The reality of the season could fall within that range, or it could surge past the upper bound by a significant margin. The models, trained on a world that was, simply do not know. This shifting baseline is far more than a point of academic interest, as it directly influences the power of the storms that form. A warmer starting point does not simply mean a greater number of storms, it means that each storm has access to a greater reservoir of energy. With more energy to draw upon, these weather systems can behave in ways grounded in the physics of fluid dynamics and thermodynamics that were previously not possible for storms with less fuel. The theoretical limit on a hurricane's intensity is not a fixed number. It is a dynamic ceiling that rises and falls with the temperature of the ocean beneath it. This brings us to the one variable that can alter the entire equation. Let us state this plainly, as it forms the bedrock for everything that follows. The amount of ocean heat available within the Atlantic basin in a year like 2026 surpasses the heat that was present during any of the three major analog years we have considered. This is not a marginal or insignificant increase. It is a substantial leap, one that has the power to change what those past seasons can teach us. This single variable is what breaks the comparison, creating a difference akin to running a new experiment that only happens to resemble an old one on the surface. To grasp why this is so critical, one must understand a concept known as maximum potential intensity. Among hurricane researchers, this concept is often abbreviated as MPI. It represents a theoretical calculation that determines the absolute strongest hurricane that could possibly form in a specific environment. This calculation is based on factors like the ocean's surface temperature and the temperature of the upper atmosphere, among other parameters. In essence, MPI acts as the ultimate speed limit for what a hurricane can become at a given time and place. It is not a forecast that a storm will reach this intensity. Most do not, due to atmospheric interference and other inefficiencies, but it is a hard upper boundary. No storm can grow stronger than the MPI of its environment allows. The maximum potential intensity is directly and powerfully dependent on the temperature of the ocean. As the ocean's temperature climbs, the MPI climbs with it. While the relationship is not perfectly linear, a useful rule of thumb is that for every 1 degree Celsius of warming in the ocean, the maximum potential wind speed increases by roughly 5%. A 5% increase might not sound dramatic, but its consequences are: the destructive power of a hurricane does not scale linearly with wind speed. It scales with the square, or even the cube of the wind speed, depending on the type of damage being measured. This means a 5% rise in wind speed can translate to a 15% to 25% increase in destructive potential. We are observing this in an Atlantic basin that is currently running 1 to 2 degrees Celsius above the long-term average in vast regions, with some areas experiencing even more significant anomalies. So, when we state that a season like 2026 is a degree or two warmer than its historical analogues, we are not merely observing that it is a little warmer. We are saying that the absolute ceiling for hurricane intensity is meaningfully higher than the one that existed in 2005, 2017, or 2020. This suggests that the strongest possible storm of the season could be more powerful than the strongest storms from those years. Hurricane Maria's winds reached 175 miles per hour, while both Wilma and Dorian peaked at 185. Could a storm in this new environment exceed those staggering intensities? Based on current ocean temperatures, the MPI calculations indicate that yes, it could. Whether this will actually happen depends on a confluence of other factors, but the potential itself is higher than it has been before. There is another, non-linear element to this that is crucial to understand. Hurricanes function as heat engines. Like all such engines, their efficiency is determined by the temperature difference between their hot and cold reservoirs. For a hurricane, the hot reservoir is the warm ocean surface, and the cold reservoir is the upper troposphere, the high-altitude air where the storm exhausts its heat. As the ocean warms, the temperature gap between these two reservoirs grows, making the entire engine more efficient. This increased efficiency means more of the available heat energy is converted into powerful winds. We are therefore facing two compounding factors. Not only is there more absolute heat available, but the storm's engine is also better at converting that heat into destructive force. This is precisely where the linear assumptions that often frame discussions about climate and hurricanes begin to break down. It is easy to hear that the ocean is 1 degree Celsius warmer and assume that hurricanes will become just 1 degree Celsius worth more dangerous. But that is a profound misunderstanding of the physics involved. The relationship is non-linear. It follows a curve that bends upward. We appear to be sitting at a point on that curve where the bending is becoming much more pronounced, and small changes are beginning to yield disproportionately large consequences. This is also why the very method of analog forecasting is starting to unravel. This approach fundamentally assumes a stationary climate, one where the conditions of 2005 and 2026 are functionally equivalent if they show the same temperature anomaly relative to their own long-term averages. But the long-term averages themselves are not the same. The baseline reference period for 2026 is substantially warmer than the one used to measure 2005. Therefore, a +1 degree Celsius anomaly today is being added on top of a baseline that is already hotter than the one 2005 operated from. The total absolute temperature is higher, and it is this absolute temperature, not the anomaly, that determines the maximum potential intensity. The analogy that comes to mind is of someone attempting to run the same experiment, but this time with significantly more fuel in the system. Imagine a chemistry experiment. You meticulously measure the same ingredients in the same proportions as a previous trial. The conditions and procedure are identical, but with one change. Instead of 1 beaker of solvent, you begin with 2. While the fundamental chemistry is unchanged, you would anticipate a reaction that is recognizable yet far greater in scale. More heat, more gas, more energy released. This is the difference between 2026 and its historical analogues. The recipe is the same, but the sheer volume of a key reactant has changed, and that single variable alters the entire outcome. This analogy raises a fundamental question about our atmospheric reference points. Do the analog years we have treated as the ceiling for hurricane activity still represent the upper bound of what is possible? Or are they simply markers along a trajectory that has since surpassed them? If the latter is true, as a growing body of data suggests, then a season like 2005 or 2020 might no longer define a worst-case scenario. Instead, it could represent something closer to a new standard for an active year, what a powerful season now looks like, rather than what the most extreme seasons once were. It is crucial to be clear here. This is not a prediction. It is an exploration of a possibility that is consistent with the data we possess. The most honest statement is that the current conditions in the basin lack a clean historical parallel. This is an observation about the present, not a definitive forecast of the future. That future could still unfold, with impacts similar to 2005 or 2020. But it could also produce something we have not yet had to describe. The position held by the most astute forecasters is one of deep uncertainty. In this context, however, uncertainty is not reassuring. It signifies that the upper range of plausible outcomes is higher than it has ever been. While the average outcome might be similar to past extreme years, the tail risk has grown, and in a system where tail outcomes are catastrophic, an increase in that risk is the single greatest cause for concern. This line of reasoning brings us to a phenomenon that connects every element we have discussed: the ocean's depth, the atmospheric configuration, the NPI calculation, and the analog comparisons. It all converges on a process that has emerged as the single most critical operational worry in modern hurricane forecasting. And it is a process that the conditions of 2026 seem almost perfectly configured to generate. We are now in Part 9, the era of rapid intensification. Rapid intensification, known by the shorthand RI, has a technical definition: a storm whose maximum sustained winds increase by at least 35 miles per hour in a 2-4 hour period. But this clinical description belies its true impact. In simpler terms, it is what occurs when a moderate storm overnight transforms into a potential catastrophe by the next morning. It represents the single most dangerous trend in modern tropical meteorology. It is also a trend whose frequency has roughly doubled since the 1980s, and the Atlantic Basin in 2026 is primed to produce it on a scale that may be unprecedented. To understand why rapid intensification has become so much more frequent, we must first appreciate how hurricanes normally limit their own growth. As we explored earlier, a storm moving across the ocean churns the water, pulling cooler layers up from below. This naturally dilutes its own fuel supply. The strengthening process is therefore inherently uneven. A storm gathers power for a time, then runs into the cooler water it has just surfaced, forcing it to pause or move on before it can intensify again. In a normal ocean, this feedback mechanism constrains the pace of development. In an ocean where the layer of warm water is exceptionally deep, however, this natural feedback breaks down. The water that the storm churns to the surface is no longer cool enough to act as a brake. The fuel supply is not diluted. The storm is free to continuously draw energy from a vast, deep reservoir. With this limiting feedback gone, the rate of intensification can accelerate far beyond what was historically possible. Storms that in previous decades might have taken 3 or 4 days to grow from a tropical storm into a major hurricane can now complete that dangerous journey in 24 hours or less. The data supporting this trend is striking. Multiple studies have shown that the proportion of Atlantic tropical cyclones undergoing rapid intensification has approximately doubled since the late 1970s. The probability that any given storm on any given day will rapidly intensify has gone up. The number of storms reaching Category 4 or 5 status from a starting point of a tropical storm, or Category 1 inch less than 72 hours, has also increased. This trend is consistent across the satellite record, across various analytical methodologies, and across different research groups working independently. The rapid intensification era is real, and we are living in it. This development tracks almost perfectly with the oceanic changes we have been describing. The ocean has warmed, the depth of its warm water has increased, and as a result, the cooling feedback has been weakening. The operational consequence is that a greater number of storms are intensifying much faster than they used to. The physical mechanism is exactly what scientific models would predict, and the observational data is precisely what we would expect to see if that mechanism is correct. Now, let us apply this knowledge to the conditions of 2026. We see an Atlantic basin where these deep, warm layers are not just present, but are a basin-wide feature. The Caribbean is loaded with thermal energy. The loop current is charged. Significant portions of the open Atlantic are similarly primed. This means the conditions for rapid intensification are not just locally favorable, they are pervasively favorable. The consequence is that the probability of any given storm undergoing rapid intensification is higher than in any prior season, and therefore, the expected number of storms that escalate from a tropical storm to a major hurricane in under 24 hours is also higher. And here we find the part of the story that is most unsettling. The primary operational result of rapid intensification is the collapse of forecast lead time. When a storm strengthens slowly, forecasters have time to recognize the trend, communicate it, and allow people in its path to prepare or evacuate. But when a storm intensifies explosively, particularly in the final 24 to 48 hours before landfall, that lead time evaporates. The storm that arrives is a much stronger and more dangerous entity than what was forecast just a day before, leaving communities with a terrifyingly small window to react. When a storm's intensity grows faster than our ability to predict it, the consequences can be devastating. A hurricane expected to be a Category 2 suddenly becomes a Category 4, leaving little time for those in its path. Evacuation orders are issued too late, and structures built to withstand a lesser storm are overwhelmed. In these scenarios, the human cost is determined not by the hurricane's final power, but by the astonishing speed at which it attained that power. We have witnessed this alarming pattern unfold repeatedly in recent years. In 2021, Hurricane Ida escalated from a Category 1 to a Category 4 inches under 24 hours before making landfall in Louisiana. 2 years later, in the eastern Pacific, Hurricane Otis exploded from a tropical storm into a catastrophic category, 5 inches, just 12 hours, leaving Acapulco in ruins. The list of such events continues to grow, with Hurricane Idalia and Hurricane Lee in 2023 and Hurricane Beryl in 2024, which became the earliest Category 5 Atlantic hurricane ever recorded. Each event is another data point confirming that storms in the modern Atlantic are not only becoming stronger, but are reaching their peak strength with unprecedented velocity. For a season like 2026, with the basin so primed, the likelihood of multiple rapid intensification events is exceptionally high. While some may churn harmlessly over the open ocean, affecting only shipping lanes, others will inevitably approach land. When they do, the fate of coastal populations hinges on whether the forecast can outpace the storm itself, a race that our forecasts are increasingly losing. This brings us back to the central theme of our journey, as the implications for the 2026 season become starkly clear. The phenomenon of rapid intensification matters so profoundly because all the conditions we have detailed, the exceptionally warm ocean, the deep reservoir of heat, a favorable atmospheric configuration, the transitional ENSO state, low wind shear, and a broken cooling feedback loop are precisely the ingredients that fuel it. The Atlantic Basin is not merely charged with the energy to create more powerful hurricanes. It is loaded with the potential to make them develop faster than ever before. The operational consequence is not just a season with more intense storms, but a season where the hurricanes that do form offer significantly less warning as they strengthen. This reality means lead times will shrink, the window for preparation will narrow, and the difference between a life-saving decision and a tragic one could be measured in mere hours, not days. This raises a critical question about whether our current systems of warning and preparation can adapt to this accelerated timeline. Over the course of our exploration, we have assembled a detailed picture of the conditions in the Atlantic Basin and the atmosphere above it. The ocean is holding more heat than at any point in our recorded history. The depth of this warmth is unprecedented. The atmospheric patterns mirror those of the most destructive seasons in modern memory. Crucially, the natural cooling mechanisms that typically restrain a storm's ultimate power appear to have failed. The result is a scenario that makes the historical analog years seem like faint precursors to what might now be possible. Yet, there is one final piece of this puzzle, a fundamental question that must be confronted to truly grasp the forces at play. Everything we have described, the supercharged ocean, the conducive atmosphere, and the trend of rapid intensification, points toward a possibility that the operational forecasting community is hesitant to address directly. This is the unsettling prospect that the Atlantic Basin has not just experienced a series of unusual years, but has shifted into an entirely new and persistent state, a new regime where our entire forecasting system, which is built on the assumption of a stable climate, may no longer be a reliable guide. This is the question we will now explore, and the answer, depending on one's interpretation of the data, may be the most consequential of all. Within the operational forecasting community, a profound question quietly persists, one that few are willing to ask aloud due to its difficult implications. The question is not whether the Atlantic is having a particularly bad year, or if the current season is an anomaly. It is whether the entire hurricane basin has structurally shifted into a state fundamentally different from the one we have known throughout the entire instrumental record. In essence, have the underlying rules of the system changed? To approach such a monumental question, the evidence must be allowed to accumulate and speak for itself. Since approximately 2017, the Atlantic Basin has generated a continuous series of above-normal hurricane seasons. Not every single year has set a new record. 2019 and 2022, for instance, had relatively few major hurricanes, largely due to the influence of a strong El Niño in those years. However, the overarching trend viewed through any moving average of recent activity, is undeniably upward. The metrics all point in the same direction. Storm counts are rising. The number of major hurricanes is increasing. Accumulated cyclone energy, or ACE, a comprehensive measure that integrates the wind speed and duration of every storm in a season, is also on the rise. Similarly, the power dissipation index, which places a greater weight on the most powerful storms, is trending upward. It seems that nearly every metric that can be constructed from the available data tells the same story. The Atlantic Basin is, on average, more active than it used to be. One could attribute this heightened activity to the warm phase of the Atlantic Multi-Decadal Oscillation, or AMV, which we are currently in. Historically, warm phases of the AMV do produce more active seasons, and this explanation is certainly valid. However, the sheer magnitude of the recent surge in activity is not fully explained by the AMV alone. The warm phases of previous decades, such as the period from the late 1940s through the mid-1960s, were active, but not to the degree we have witnessed since 2017. This suggests that something else, an additional forcing, is layered on top of the AMV's natural cycle. Beyond the sheer number of storms, another, more subtle signal emerges from the data when we examine the proportion of storms that achieve major hurricane status. This metric, which is independent of the total storm count, reveals a different aspect of the basin's behavior. In any given season, there can be many weak storms, a few strong ones, or some combination. But the fraction of storms that intensify to Category 3 or higher serves as a direct measure of how favorable the environment is for intensification. Over the past decade, this proportion has been steadily climbing. This tells us something crucial. We are not just observing more storms in total, we are seeing a higher percentage of those storms grow into the most dangerous major hurricanes. This indicates that the Atlantic Basin is not just becoming more conducive to storm formation in general, but is specifically becoming a more efficient engine for producing the most intense and destructive weather systems. Another key metric, the Power Dissipation Index, has also been steadily rising throughout the satellite era. Because this index gives greater weight to more powerful storms, it can reveal an increase in destructive potential, even when the total number of storms remains the same. In the Atlantic, the climbing PDI suggests that each season is, on average, generating more total destructive power, regardless of fluctuations in the count of named storms. When we combine this trend with the observations of more frequent storms, a greater proportion of major hurricanes, and more instances of rapid intensification, a profound question begins to emerge. Are we merely witnessing a series of unusually active years? Or is this evidence of a more fundamental state change, a shift into an entirely new and structurally different climate regime? This leads to a compelling hypothesis that deserves serious consideration. For much of our recorded history, the development of Atlantic hurricanes was primarily limited by the availability of ocean heat. The ocean contained areas of both warmer and cooler water, and a storm could only form when atmospheric conditions were favorable over one of these warm patches. The ocean provided the necessary foundation, but the atmosphere with its wind shear, dry air, and instabilities acted as the ultimate trigger, dictating the rhythm of active and quiet periods. But what if that fundamental relationship has changed? The evidence now suggests that ocean heat may have ceased to be the primary constraint. With so much thermal energy stored so consistently and at such great depths across the basin, the fuel for hurricanes is essentially always present. The bottleneck has effectively shifted. In a system where the ocean's energy is no longer a limiting variable, the atmosphere becomes the paramount factor. In this new paradigm, it is the atmosphere that holds all the cards. In this new reality, atmospheric factors like wind shear, the Madden-Julian oscillation, and the Saharan air layer would become the dominant controls over hurricane activity. Because these variables operate on much shorter timescales than the ocean, Their new prominence carries profound implications for forecasting. Our seasonal forecasts, which are released each spring, have long been built on the assumption that the long-term state of the ocean can reliably predict the activity of the coming months. But if the ocean's condition is no longer the most relevant variable, the reliability of these forecasts could diminish. The predictive signal from the ocean would weaken and the margins of error would grow. This would force a greater reliance on short-term atmospheric forecasting, which is dependable only on timescales of a few weeks at most. We could be entering an era where the 6-month outlooks, which tell us what to expect for the season, become less informative than they have ever been. This potential shift also challenges the practice of analog forecasting, which works by comparing current conditions to similar years in the past. That method is only valid if the underlying climate system remains stationary. If the Atlantic has truly entered a new operational mode, then comparing it to analog years from a previous regime may no longer be a meaningful exercise. The very patterns we look for might not carry the same predictive weight they once did, and the history we rely on for context may become increasingly irrelevant. The unsettling conclusion is that we may be losing our clean historical comparisons. We could be observing a basin that is structurally different from anything humanity has ever measured, and we may have to do so without the familiar historical framework that has always guided our understanding. This is a possibility that forecasters are quietly grappling with, even if it is not yet part of the public discourse. This brings the focus directly back to the central question of the 2026 season. The reason this matters so profoundly is that 2026 might not simply be a more extreme version of a season like 2005. Instead, it could be the very first season that must be analyzed as a member of this new, unfamiliar regime, the inaugural data point for a category we did not even know we were creating. If that turns out to be the case, then the upper boundary of what is possible becomes a true unknown. This is not because of a failure in the science, but because our historical data simply does not contain the scenario we now find ourselves in. So, we are left with a critical question. Has the Atlantic Basin truly entered a new state? The honest answer is that we may not know with certainty for several more years, as such fundamental shifts are always easier to identify in retrospect than in the moment. However, the existing data is remarkably consistent with this hypothesis, and if the hypothesis proves correct, then the 2026 season will be one of the key events that helps to define what this new normal actually looks like. But there is one final piece of evidence to consider, and it may be the most compelling of all. The case for a regime shift becomes significantly stronger when we broaden our view beyond the Atlantic and look at the planet as a whole. What is unfolding in the Atlantic is not an isolated event. The same kinds of alarming signals are beginning to appear in other ocean basins around the world, and this wider context provides the strongest indication yet that something of global significance is underway. A powerful example of this occurred just a few weeks ago, an event that may have gone largely unnoticed by the public, but sent ripples through the meteorological community. In April of 2026, a storm named Typhoon Sinlaku formed in the Western Pacific. It intensified to become a super typhoon, a designation for storms with sustained winds of at least 150 miles per hour, the Pacific's equivalent of a Category 4 or 5 Atlantic hurricane. For a storm to reach this intensity at any time of year is notable. For it to happen in April is almost unheard of. After a meticulous review of historical data, Sinlaku was confirmed as the most powerful April typhoon ever observed in the Western Pacific. This was not merely the strongest in a decade or in living memory, but the most intense for that month in the entire continuous instrument record for that basin, a record built from decades of data, from satellites, reconnaissance aircraft, and ocean buoys. An event of this magnitude is something we would expect to see perhaps once in 100 years, or possibly even less frequently, raising the question of what such an anomaly means in the context of our changing world. Statistically, an event of its kind should not occur within our lifetimes. Yet, just a few weeks ago, it did. This record-setting storm went almost entirely unnoticed outside of professional meteorological circles, a ghost in the global news cycle. Its story was missed largely because it unfolded over a region of the world that rarely captures the focus of Western media, and because it mercifully dissipated before making a catastrophic landfall that would have forced its way into our headlines. The storm, named Sliku, simply happened. A new record was set, logged into a database, and the world continued on its way. But the story of that storm is profoundly important for our conversation. It formed and intensified over the very same kind of ocean environment we have been exploring. The waters of the Western Pacific that fed Sliku were anomalously warm, with deep layers of heat, creating an energy surplus that has no parallel in the historical record. This is the same thermal fingerprint we are now seeing in the Caribbean, the same one off the coast of West Africa, and the same one within the Loop Current. It raises a quiet but urgent question. What does it mean when nature produces such an extreme event and we are not even watching? This storm was no accident, nor was it a statistical outlier in a stable system. It was the direct and predictable consequence of an ocean that contained far more energy than our historical records can account for. In turn, it produced a result that also has no precedent in those records. This is not a coincidence, and it is certainly not an isolated incident. It is tempting, when hearing of a record-breaking event in a distant part of the world, to file it away as someone else's problem geographically remote and unrelated to our own immediate surroundings. But that instinct is incorrect here. The same elevated ocean temperatures we are tracking in the Atlantic are now appearing in every other major basin. The Western and Eastern Pacific, the Indian Ocean, and the Southern Oceans are all showing signs of unusually high heat content during their respective cyclone seasons. Every single tropical cyclone basin on the planet is affected. The energy surplus is not a regional anomaly. It is a global phenomenon. This distinction is perhaps the most critical point of all, as it fundamentally changes how we must interpret these events. If we were to look only at the Atlantic, we could construct a narrative where what we are witnessing is a regional fluke. It would be easy to blame a temporary, unlucky alignment of basin-specific factors, perhaps suggesting they might realign for the better next year. You could point to the warm phase of the Atlantic Multidecadal Oscillation, or AMV, and say that explains it. You could cite the weakening of the Atlantic Meridional Overturning Circulation, the AMOC, as the cause. You could even argue that an insufficient winter mixing of the basin is the culprit. And all of these factors are, to some extent, true. They are real and measurable parts of the story. But they cannot be the whole story, because the full story is far bigger than the Atlantic Ocean. The implications of this global pattern are significant. If only the Atlantic were showing this level of heightened activity, one could reasonably argue that it is a regional issue, driven by the unique geography and circulatory patterns of the North Atlantic. Those factors, like the AMV and AMOC, are undeniably present in the data. However, the fact that the same general heat signals are appearing simultaneously across multiple, unconnected ocean basins strongly suggests that the underlying driver is not regional, but global. The entire ocean system, across the whole planet, is now operating with more energy than it did in the past. This means the Atlantic's current, elevated state is unlikely to revert to a cooler, historical baseline anytime soon. The fundamental forces loading the Atlantic with excess heat are the same forces at work in the Western Pacific. They are the same forces that can produce a 100-year typhoon in April. They are the same forces sitting beneath every part of the global ocean that we can measure. This realization forces us to ask what this means for the very tools we use to predict our future. Consider for a moment what this does to our forecasting framework. For decades, this framework has been built on the core assumption that warm anomalies are temporary deviations from a stable, long-term baseline. The Atlantic gets warm, but it eventually cools. The Pacific heats up, and it too eventually cools. The basins are expected to fluctuate around their long-term averages, but the averages themselves are assumed to be stable. This assumption is what makes seasonal forecasting possible in its current form. Forecasters compare the present state to that long-term average, measure the deviation, and then predict consequences based on how the climate has responded to similar deviations in the past. The entire system depends on that average being a fixed, reliable anchor. But what if that long-term average is no longer stable? What if the baseline itself is moving? If the average we are measuring against is drifting upward year by year, our calculations may not be capturing the full reality of the situation. In that case, our modern anomalies are not just temporary excursions from a fixed point. They are instead points along an ongoing trajectory. The baseline for next year will likely be a little warmer than this year's, and the year after that, warmer still. The historical analog years we rely on for comparison will recede further and further into the past, appearing similar in our calculations only because those calculations assume the baseline has not moved. This is precisely what the global signal is telling us. The baseline has moved, and it is still moving. The deviations we measure are now a composite signal, partially capturing true anomalies and partially capturing the unseen drift of the baseline itself. This means our forecasting framework, while using the same math, is becoming subtly but significantly less reliable with each passing year. The data feeding the models is shifting on a foundation we once thought was solid. Finally, there is a piece of fringe science worth mentioning, as it occasionally surfaces in conversations about elevated ocean energy. Some researchers have pointed to solar cycle factors as a potential contributor. We are currently near the peak of solar cycle 25, which has been notably more active than the preceding cycle 24, one of the weakest in the modern record. The argument suggests that increased solar output during these peaks contributes to ocean heating in subtle ways, and that some of the recent warming is attributable to our place in this one-year cycle. However, the mainstream scientific view, based on the available evidence, is that the solar contribution is small relative to other drivers, particularly anthropogenic greenhouse forcing. For now, that consensus view appears to be correct. The sun's activity, while not zero, is just one piece of a much larger and more intricate puzzle. In a year where numerous environmental factors seem to be converging, even minor contributors warrant our attention. We are witnessing more than just a solar maximum. It is a peak that coincides with a persistent, long-term warming trend. This is further compounded by a regional Atlantic anomaly and a global ocean signal that has been intensifying for years. It is a powerful reminder that when many small forces push in unison, their collective impact can become immense. It is important to clarify that the solar cycle is not the sole explanation. It is one variable among many, and likely not the most significant. However, to disregard it, as some analyses do, is to miss a crucial aspect of our current situation. We are not in a moment defined by a single dominant variable, but by the reinforcement of many. The Atlantic multi-decadal oscillation is in its warm phase. The Atlantic meridional overturning circulation may be weakening, and vertical ocean mixing has been less effective. The preceding winter failed to reset the basin's heat. The Pacific is transitioning between El Niño and La Niña, and the global ocean as a whole is brimming with surplus energy. And through it all, the sun is operating at the upper end of its one-year cycle. No single one of these conditions is sufficient to explain what we see, but taken together, they create the very picture that is now coming into focus. The purpose of introducing this global context is not to offer a separate treatise on planetary ocean heat. While that is a vast and important topic, our focus here remains fixed. The key is to connect this broader planetary signal back to the central theme, the possibility that the 2026 Atlantic hurricane season could emerge from a baseline with no true historical parallel. This global energy surplus tells us that the conditions we are seeing are not a statistical fluke or a temporary anomaly. This is not simply a year where the dice have rolled unfavorably. Instead, it appears to be part of a planetary state of elevated ocean energy, a condition that has been building over time and will persist regardless of the actions of any single weather system. The Atlantic is not merely experiencing an isolated bad year, it is actively participating in a worldwide phenomenon, and it is this larger condition that will form the backdrop against which the 2026 season will unfold. This brings us to a familiar point of discussion whenever such topics arise: the temptation to view an extreme event in isolation and dismiss it as mere weather, rather than a signal of a larger shift. A single typhoon, like Sinlaku, viewed by itself, could indeed be argued away as a random occurrence. Yet, that argument begins to dissolve when placed alongside the other extreme events of the last few years. Consider the earliest Category 5 Atlantic hurricane ever recorded, or the most powerful landfalling Pacific hurricane in modern memory. Think of the multiple, unprecedented marine heat waves appearing in ocean temperature data, and the complete breakdown of typical seasonal patterns in one ocean basin after another. While any one of these could be individually labeled a fluke, their collective appearance tells a different story. Together, they are no longer random outliers. They represent a new baseline reality, asserting itself one broken record at a time. Sinlaku is not the whole story. It is but one data point in a narrative being written across every ocean on our planet. So when we question whether our historical analogues are sufficient for understanding what lies ahead, this global signal provides one more reason for skepticism. This is not a minor detail. It may be the single most compelling reason to doubt the adequacy of our analog framework. The historical years we use for comparison simply did not unfold within the context of a globally elevated ocean state of this magnitude. They occurred against a backdrop that was, in absolute terms, cooler than our present one. The Atlantic anomaly in 2005, for instance, was a powerful regional event set against a more or less normal global baseline. The projected Atlantic anomaly for 2026, however, is a regional event developing on top of a global one. It is an anomaly stacked upon an anomaly, a surplus built upon a surplus. The fundamental energy budget is simply not the same. In absolute thermodynamic terms, the system has far more energy to work with than any of our prior reference points. This is what makes the current situation so difficult to compare to anything in the historical record. The historical record contains no year where a regional anomaly of this scale coincided with a global anomaly of this intensity. It simply does not exist. We can find warm Atlantic years in the records, and we can find warm global years. What we cannot find is a year where a profoundly warm Atlantic was superimposed upon a global ocean carrying this much surplus energy. We are navigating new territory. Consequently, the very language of the analog framework, which presumes we can locate a roughly equivalent year to use as a guide, begins to fail when no such year can be found. We are, both literally and figuratively, sailing into uncharted waters, and we are doing so without the familiar navigational charts that have guided us for decades. Ultimately, this global signal is perhaps the single most compelling reason to view the 2026 setup with profound seriousness. It is more significant than the surface temperatures alone, more telling than the depth of the warm water, and more fundamental than the transition between ocean-atmosphere patterns. This global signal is the reason this is not just a typical bad year. It is the reason our historical analogues may fail to contain what is possible. And it is the reason the next year will likely begin with a higher energy baseline than this one, and the year after that higher still. It explains why every season for the foreseeable future must be evaluated against a baseline that is no longer static. We are not just observing a single year, we are witnessing one moment in a much longer process, a process that is only just beginning. This leads us to the final piece of our analysis, where all the threads we have been following must come together. All the conditions we have described, the loaded ocean, the favorable atmosphere, the disrupted feedback loops, the global energy surplus, constitute the setup. They represent the vast potential energy that has been accumulating over months and years, a state that will not reverse itself before the season begins. But what we have not yet discussed in detail, the element that will ultimately determine what happens in the months ahead, is the trigger. And it is with the trigger that all the conditions we have spent so long examining must confront the inherent limits of our predictive abilities. Because unlike the state of the ocean, the trigger is not something we can see months in advance. The trigger is the great unknown we are about to discover. Let us return to the fundamental observation that began our journey, to the very first point we established. At the end of April, well before the hurricane season officially commenced, the Atlantic Ocean was already exhibiting characteristics typical of August. Everything we have examined, from the oceanic data and atmospheric mechanics to analog comparisons and regime shifts, converges on a single, undeniable conclusion. The ocean is primed for activity. We have seen this exhaustively in the data. The fuel for powerful storms is already present in the basin, an immense reservoir of energy waiting to be tapped. The conditions for an extreme season are in place to a degree that far exceeds any prior baseline we have on record. This is not a subtle signal, one that requires squinting at the data to discern. It is an anomaly visible in every metric, across every measurement system ever aimed at the basin. And it is so consistent that even the most conservative forecasters, those whose profession demands they avoid overreaction, have ceased using the word normal. However, an energized ocean does not, by itself, generate hurricanes. The ocean provides the foundational platform, the vast, slow-changing stage upon which everything else must unfold. It is the atmosphere that acts as the trigger, activating the potential stored within the water. The atmosphere determines whether that available energy becomes organized into storms. It dictates when that organization happens, where the storms travel once they form, and how powerful they become before encountering land. In this dynamic, the atmosphere is the unpredictable catalyst. While the ocean evolves over weeks and months, the atmosphere can completely reconfigure itself in days. The entire narrative of a hurricane season is written in the gap between what the ocean offers and what the atmosphere chooses to do with it. It is here that we must be honest about the limits of what is knowable. A core responsibility of any scientific explanation is to clearly define the boundaries of predictability. At this moment, I cannot tell you which weeks of the season will be active and which will be quiet. I cannot say where the storms will form, what tracks they will follow, or which specific coastlines they will ultimately threaten. It is impossible to know whether the coming season will produce 20 named storms or 30. It is equally impossible to say if the United States will face a major hurricane landfall or escape unscathed. Will the Caribbean be devastated or spared? Will the Gulf Coast witness another event on the scale of Katrina, or will all the storms curve harmlessly out to sea? None of these outcomes can be predicted months in advance. The system is simply too chaotic, the variables too numerous. The only truthful answer to these questions in late April is that we do not know. Anyone who claims otherwise is not dealing in facts. What we do know, however, is the part of the equation that does not depend on these atmospheric wildcards. We know that the background conditions for any individual storm that does form are unprecedented in the modern instrumental record. We know with certainty that any storm will have access to more thermal energy than any storm in our historical analog years. We know that the wind shear environment is projected to remain favorable through the climatological peak of the season, the crucial 8-week window when the most destructive storms historically occur. Furthermore, we know that the conditions supporting rapid intensification are not confined to isolated pockets, but are pervasively favorable across most of the main development region. The natural cooling feedbacks that have historically put a cap on storm intensity have broken down across vast stretches of the basin. All of this is in the data right now, a clear signal of a system that is structurally hotter and more energy-rich than anything for which we have a clean historical comparison. This brings us to the specific uncertainties, the key variables that will ultimately determine whether this season is bad, very bad, or something for which we have yet to find a description. The first is the timing of El Niño's atmospheric arrival. If El Niño's influence develops faster than current models suggest, the resulting suppressive wind shear could arrive earlier than the season, analogs predict, potentially moderating the season. The peak could pass without the wildcards aligning often enough to produce a catastrophe. If, on the other hand, El Niño develops more slowly or stalls in its transition, the Atlantic could remain highly favorable for storm development through October or even into November. The historical record is mixed on which outcome is more likely in a setup like this, and forecasters are monitoring this transition week by week. Another critical uncertainty, one that receives less public attention than it deserves, is the distribution of wind shear across the basin. Even within an overall favorable environment, the ocean is not a uniform field of low shear. There are regions where shear is naturally higher and corridors where it is lower. The precise spatial distribution of these low shear pathways strongly influences where storms can form and what tracks they can maintain. Small, seemingly minor differences in the location of these corridors can shift the focus of an entire season from one set of coastlines to another. Whether the path of least resistance runs through the central or western Caribbean, extends deep into the Gulf of Mexico, or favors tracks that curve away from land are details that determine where impacts are felt, yet they are impossible to predict months in advance. Finally, we must consider the steering patterns. Even when powerful storms form, their ultimate destination is dictated by the position and strength of the Bermuda High and the upper-level wind patterns over North America. Some seasons feature steering currents that drive storms primarily into the Gulf of Mexico, threatening Texas, Louisiana, and the Florida Panhandle. Other seasons have patterns that cause storms to recurve out to sea before they reach land, sparing the coast almost entirely, despite high overall activity. Still others feature patterns that guide storms up the East Coast, threatening the Carolinas, the Mid-Atlantic, and even New England. These steering patterns are fundamentally weather scale features, evolving on timescales of weeks. Attempting to predict their behavior for the entire season from the vantage point of April is, for now, an impossible task. Even with nearly identical oceanic and atmospheric conditions, two hurricane seasons can yield vastly different results, determined simply by the steering currents that guide the storms. This inherent variability means that viewing the 2026 season through a simple binary lens, active versus quiet, or bad versus good, is misleading. A more accurate framework is one of probability. For the season ahead, the entire distribution of potential outcomes appears shifted toward the more severe end. This suggests that the average expectation is for a more impactful season than usual. But the most significant change lies in the extremes. The tail risk, which represents the likelihood of a truly unprecedented and catastrophic event, is now higher than in any preseason period on record. In a system where such extreme outcomes can be devastating, this increase in tail risk demands our most serious attention. While the center of the probability curve may only shift slightly, the tails where the true disasters reside can shift dramatically. This is not to say that a catastrophic season is a certainty. The final outcome will depend on the trigger, which is composed of several atmospheric wildcards. It is still possible, though perhaps unlikely, given the underlying conditions, that these variables will fail to align for a destructive season. The Madden-Julian oscillation might enter a suppressed phase during key periods, or high levels of Saharan dust could inhibit storm formation at the season's peak. It is also conceivable that steering patterns could direct storms harmlessly out to sea, leading to minimal landfalls, even with elevated offshore activity. A scenario where the basin is loaded with potential, but ultimately misfires has happened before and could happen again. Yet, the opposite scenario is also possible, and based on the pre-season setup, perhaps more likely than ever before. This would be a season where the wild cards align perfectly. The MJO could produce favorable phases over the Atlantic during the peak, Saharan dust could remain low through the active months, and a robust African easterly wave train could generate one seed disturbance after another. If the steering patterns then thread these storms directly into populated coastlines, the consequences could be staggering. Against the backdrop of an ocean that is hotter and deeper than any analog, the outcomes could exceed anything in modern memory, not by a small amount, but by a margin that would force us to revise what we thought the upper bound of an Atlantic hurricane season actually is. The crucial insight is not to predict which of these specific scenarios will unfold. Rather, it is to recognize that the spectrum of possibilities is wider, and the risk of an extreme outcome is greater than has ever been recorded in a pre-season assessment. The system is loaded in a way that maximizes the consequences of every variable that activates it. Every favorable wildcard hits harder. Every storm that does form has more potential. Every rapid intensification event has deeper fuel to draw on. This setup amplifies whatever the atmosphere chooses to do with it. That is the fundamental nature of the situation we now face. This brings us to a crucial conclusion about our ability to forecast what lies ahead. The historical analogues we rely on may no longer be a sufficient guide for what 2026 is capable of producing. These past examples were established in a climate regime where the upper boundary of possibility was simply lower. They are useful as floor estimates, but they are likely no longer useful as ceiling estimates. The worst seasons in the analog record, 2005, 2017, and 2020, may be the kind of season that 2026 is most likely to resemble. They may also, in the worst case, be the kind of season that 2026 exceeds in ways we have not had to describe before. It raises the sobering possibility that by November, we may find ourselves searching for a new vocabulary, for new classifications, to describe what we just watched the basin do. To say the system is primed beyond historical precedent is perhaps the most honest assessment of our current reality. The ocean is loaded beyond what any analog year had. The atmospheric trigger is in a configuration that historically produces extreme seasons. The cooling feedbacks have broken down. The rapid intensification trends are accelerating, and the broader global ocean is in an energy surplus state. This means the Atlantic is not just having a bad year, but is participating in a planetary signal that is unlikely to reverse course in time to moderate this season. Every layer of the system is pulling in the same direction, with none pulling against the others. That is what makes this different from a year that is just warm. This leads back to a central, defining idea about our present moment. The 2026 Atlantic hurricane season is not waiting to build. It is not in some pre-season cooling state where it will gradually ramp up over the spring and into the summer the way past seasons have. The building is done. The energy is in the basin. The setup is in place. The season is not waiting to build. It is simply waiting to begin. And when it does begin, Sometime in the next 4 to 6 weeks, we will start to see how this loaded system fires. We will start to see whether the analogues we have been holding on to are going to hold up, or whether 2026 writes a new chapter that we have to find new vocabulary to describe. We will start to see whether the regime hypothesis is right, whether we have actually crossed into a new operating mode for one of the most consequential weather systems on the planet. We will start to see what the future of the Atlantic Basin actually looks like, not as a model output, not as a projection, not as a hypothetical, but as the real, lived, observed weather of one season in real time, watched by satellites, measured by buoys, and felt by the people in its path. The forecasters are watching. The data is in the basin, the atmosphere is taking shape, and the rest of us, the people who live within reach of the storms that will or will not form over the coming months, are about to find out what a hurricane season looks like when it begins from a place that no hurricane season has ever begun from before. There is no historical version of this to lean on. There is no prior season we can point to and say, well, that one started here too. And it turned out fine. Every prior season started cooler. Every prior season started shallower. Every prior season started with a basin that was in some meaningful sense less ready than this one is. The potential is in place. The trigger is the only thing left. In the coming weeks, somewhere above the warm expanse of the Atlantic's primary storm nursery, a process is set to begin. The season's first disturbance will coalesce, born from the potent combination of thermal energy, atmospheric moisture, and our planet's own rotation. Initially, it will be a modest formation, perhaps too fleeting to even earn a name. It could vanish within a day, leaving only a minor note in meteorological records. And yet, this small event holds a deeper significance. It is the first tangible evidence of an immense energy surplus that has built silently for months, and the first expression of an ocean basin that no longer behaves as it once did. Whether this nascent system dissipates into memory or grows into a storm that history will recall by name is, for now, a complete unknown. The season will unfold, and we will observe what comes. Yet, beyond the immediate forecasts lies a more challenging consideration, one that persists after every dataset is analyzed and all uncertainties are noted. If the 2026 season is indeed the first of a new atmospheric regime, then it also serves as a preview. It becomes a template for what all hurricane seasons may resemble from this point forward, set against a constantly elevating baseline of energy. This suggests we are entering a new era of Atlantic weather, where the historical analogues we rely on for context recede ever further into a past that no longer corresponds to the present. The ocean we are observing now is not going to revert to its former state. The immense depth of warm water in the Caribbean is not going to be reset over a single winter. The global energy surplus is simply too vast to be drained in one season. Whatever 2026 becomes, the 2027 season will begin from a baseline that is at least as warm, and 2028 from one warmer still. A fundamental truth emerges from this progression. The ocean has changed, the basin has changed. And so, what we are about to watch unfold over the next 6 months is not merely one season. It is the leading edge of a future that has, quietly and without announcement, already arrived. The forecasters are aware, and the data makes it plain. In a few weeks, when that first disturbance organizes over the open Atlantic and begins its long, slow drift westward toward whatever it is destined to become, the rest of us will begin to find out what that future truly feels like.